Hi, welcome back to another video of Black Body Engineering. And in our last video, we talked about a 1-bit full adder, the core building block of arithmetic in our future 32-bit CPU design. But as we saw, chaining these adders together becomes slow because of one major issue, the carrier delay. So let's try to recall what was the full adder. Let's start with our equation. The full adder equation, if you recall, it was sum is equal to A XOR B XOR Cin. And our C out, it was A and B ended or Cin A XOR B. So if we do a really quick sketch about this circuit, it's going to look like this. And our C out is going to look like this. This is our XOR B. This is our Cn. Yeah, one more, and that is A and B. Both of the are OR together, and that is in C out. And this is our full adder. So if we take a copy of this circuit, we can see that my C out will connect to my Cn. And it's gonna be like that for the rest of my circuits. So if I put another one here, then another C out is gonna connect to my other Cn. So if you see, if there's a change here, in order to reflect that change over here, it will have to travel this way. It will have to go this way. It will have to go down. It will daisy chain to the other one, and it's gonna take the same route all the way to C out. As you can see, you already had 3 stages. This is stage 0. This is stage 1. This is stage 2. As you can see how cumbersome that can be if I have to be at stage 32. By the end, it has 1, 2. It has 2 gates here, 2 more, and 2 more. By the time it reaches stage 32, my carry has to propagate for 32 gate, for 64 gates. And if you add 64 times the gate delay delta, let's say you have to run 5 nanoseconds, 64 per delta, then we're talking about 320 nanoseconds of delay. While this only, if you see this, it's only 2 gates. So 2 gates times 5, we're talking about from here to here, it takes 10 nanoseconds. but the whole thing to reflect on the last stage is going to take 320 nanoseconds. And that is really bad because that means the whole circuit is going to depend on that 327 and 320 nanoseconds time instead of the 10 nanoseconds. So because we have this problem where our worst case is going to be 320 nanoseconds or 32 bits, a solution was implemented, and that gave rise to our CLAs, otherwise named carry, look ahead circuits. The logic is somehow complex. However, it does improve our circuit tremendously. What is going to happen is it's going to make the carry out available without the propagation. So let's recall for a second our carry out formula. So our carry out is equal to what? To both inputs A and B, or A XOR B, and end it with a C in. However, this is going to be the same for all stages. So we can generalize that formula in that CE plus 1 is equal to AI BI, this stage for what stage are you in? So, or A XOR B in C in. So if we try to divide this equation on two sides, so we can divide this into a generator and we can also say that this part is the propagation. Since the propagation is always going to depend if one of them is 1, we can replace this XOR B by an OR gate. It looks cleaner. It provides a cleaner logic representation, and our result is gonna be, some pi XOR B by Ci. Recall that this part is simply A XOR B, and then if you put this one here, it's XOR B Cn. That is the same that we have around here, that we have right here. So it really doesn't matter. However, but for cleanliness, we're gonna represent it like this. So if we try to explain this, let's rewrite this formula for a second. A BI or A XOR BI CI. Let's talk about stage 0. Stage 0, then we have C1 is equal to A0 B0 or A0 XOR B B0 C0. And if you see, this is very similar to this. I mean, it's the same because Cn for the first stage is simply C0. And this is the first bit, and this is the first bit. So we got the same. So Now that we got the first stage, we can proceed and go to the next stage. C2, A2, B2, or A2 XOR B. Oh, I made a mistake here. A1, B1, A1, B1, C1. And if you see, C1 is simply this. So if I substitute that into that equation, we obtain the following equation. A1 XOR B, B1, AO, BO, or AO XOR BO, C0. And this is going to be available to that carry out. We're not depending on the propagation. All the inputs are available at the same time at a minimum of 2 gates or 2 levels to each carry out for the next stage. Another way that we can rewrite this, because we already see the logic, is see. We can say, let's rewrite the original formula with GI, because GI is this and PI is this part. So because we know that, we can rewrite or PI CI. So C3 is equal to G2 or P2 C2. And you keep going. Sig4 G3 plus P3 C3. And then you can put this in here. And then you have G3 or P3 P2 C2. Obviously C2 is over here, but we didn't convert it, so we're just gonna leave it like that for our representation. So once we see our logic, we can see how will the header key looks. So it's very simple. We can develop something called a PFA, that stands for a partial full adder. Remember that a full adder has an X, it has a Y, it has a carry in, and it has a sum, and it has a C out. So what's going to happen is that when we don't implement the C out, but instead we implement the equations that we need. So this is a full adder, but we want to implement a partial full adder. So we have a X, we have a Y, we have a carry in, we need a carry in, we have the summation, but we have 2 additional outputs. What those outputs are? Well, remember that we have GI is equal to A and the 2BI, and PI A XOR B Y. So what we can do is, remember that this is let me keep it. This is X, this is Y, this is N, and so for GI, we need an AND gate. So we implement an AND gate with X and Y. That is going to be our GI. And our PI is already implemented right here. So we just take it from here. And that's going to be our PI. And this is the values that we're going to use to implement the next circuit. So now that we have implemented this output for our full adder, we're not going to draw this anymore. From now on, we're going to write it like this. PFA, we're going to X, Y, we'll put a C in right here if we want to. We want sum. We're going to make those outputs available for us because we're going to use them. And now we can implement our logic for our carry out. So let's say we have a 4-bit full adders. Well, P full adders. So how will this look like? Well, it's very simple, really. Instead of daisy chaining them, we're gonna proceed in the same way. We're gonna have a PFA here. We're gonna have another PFA here. We're gonna have another PFA here. And we're gonna have another PFA here. Each one has an input. You know, we need an input. So let's name this one A0, B0, A1, B1, A2, B2, A3, B3. Each one has a summation output. Each one has a carry in. However, we're gonna implement our carry look adder, our carry look ahead logic down here. This is gonna be our circuit. We're gonna name it a carry look ahead logic circuit. This is gonna have our P0, G0. Okay. This is going to be my P1, G1, P2, G2, P3, G3. And H1 is gonna, well, we need our C0. It's gonna go here. And it's gonna go to my logic, carry logic. Remember that my first one, you see, my first one is right here. So we need it. And each one is gonna make C1. So that's C1. This is C2. This is C3. And that one's gonna have a carry 4. You see, our carry out doesn't come from our PFA, it comes from the carry look ahead logic. And if we want to extend this to bigger circuit, then we need our carry logic to develop a propagate group, and we also need a generator group. So because of this concept, it's very easily to expand our circuit, because now we can make a copy of this and we can expand it to multiple CLAs. And this is what actually allows us to stack them together, providing a faster arithmetic solution. Okay, so once we have explained how to implement the CLA, now it will be very useful for me to show you how would it look in practice. So I took the liberty to implement the circuit, and this is how a 32-bit LEU looks like. You can see each one has its own summation. For the simplicity of this circuit, this is going to be my output, or I will call it result, and this is my A and B. And I have converted this from binary to signed decimals. We can see how our circuits start to add and subtract properly. So let's zoom here. Remember that we have 0, 0, that is AND gate. A 0, 1 is an OR gate, but a 1, 0 is my arithmetic. So if I go here and I put 10, you can see it's already populating. 10 plus 0 is 10, plus 20, we have a 30. And if we have a 512 plus 20, we have 532. However, if we want to subtract, then we have to negate the B, and that will be subtraction. So 512 minus 20, that's 482. And you can see the circuit, depending of what wires go true or false, it will deactivate and reactivate depending where it has to go through. It would be really nice if I can show you. Let's see, this is the internals of each component. So inside here I have an LEU of 4 bits, and inside of that I have 4 LEUs connected to the carry Lookahead, that is right here. This is the overflow logic. It's easily implemented with 1, 2, 3, 4, 5, 6, 7 gates. This is the carry Lookahead. However, I'm going to show you from the back. This is the overflow. This is the partial full adder. If you can see, my propagate is here and my generator is here. I did leave the carry out for future use in case I need it, especially for the overflow logic. I don't think I need it for unsigned, but I'll leave it just in case. This is my carry Lookahead logic. As you can see, you have the group propagate and we have the generator group. This CLA is just the same one implemented. If you can see, it's the same carry Lookahead. I don't need additional. Let's see. This is connected. This is bit 0, 1, 2, 3, 4, 5, 6, 7. Well, 0 through 4, 0 through 3, 4 times 7, all the way to bit 31. And this is bit C32. And this last bit is connected to that one. And this is my 32-bit LEU with the overflow flags in here to prevent overflowing. And it works for everything. So this is the circuit for LEU, and this will help improve with a better design for my circuit. So it's very simple. So today we transform our basic full adder into a fast, scalable unit using a carry look ahead logic. And I'm very glad because a carry look ahead is not something we study in college, at least on in the undergraduate levels. And I'm really happy. This is the first time I build it, and I was always very interested because they always teach the ripple adder, but not the carry look ahead. And in the next video, we'll try to expand and see what we can build. Hopefully, towards our 32-bit CPU. If you found this useful, go ahead, subscribe. I mean, I'll try my best to put more videos.